Often we use R to find roots of equations. This has to be done numerically because R doesn't do anything symbolically. In particular, we're going to find roots when we're finding percentiles of general continuous distributions in R. A built-in function that does this in R is something called uniroot. If you do question uniroot, bring up help, you get something which looks pretty unintelligible to start. The simple thing here is it says the function uniroot searches the interval from lower to upper for a root, that means a 0, of a function f with respect to its first argument. Let's actually do this with an example. So what I want to do is I want to solve the following equation. Cosine x equals x, for x somewhere between minus pi and pi. If we just draw a graph of this, get the following. If I can bring it over. Notice here's cosine of x, here's x. It looks like we have a root of the equation somewhere around 1. How does uniroot work? Well, first of all, uniroot only finds roots or zeros of an equation. So if we want to solve for cosine x equals x, we're going to somehow have to convert that into something where we're looking for a 0. The trick here is to look at cosine x minus x. Cosine x minus x will only be 0 if cosine x equals x. So I'm going to actually, in this case, define a function actually on the fly. Let's see how this works. Here it is, uniroot. The first argument has to be a function. It can be user-defined, as we're doing here, or it can be built in, or it could be user-defined, defined outside of the uniroot function. In this case, we're defining it on the fly, a lower limit and an upper limit. Basically, we're looking for a root of this equation somewhere between minus pi and pi. And lo and behold, we got an answer. And what's somewhat common in R for a lot of functions is it did not actually give us a number back. It gave us an R list. What we want is actually the root version of this. So our $root is actually the number 0.7390843, probably has a few more decimals of accuracy that is not being displayed. Notice it's numerical. I always like to check to see if my answer is right. Never trust the computer program if you don't have to. In this case, I'm going to take the cosine of my RC $root and I'm going to compare it to RC $root because they should be the same. And lo and behold, pretty accurate. Once again, we're doing things numerically. That's why we're not getting an exact same result. Nothing is exact in R. Everything is done numerically in the computer. Okay, so now let's solve another problem. This case will work a little differently. We want to find the 74th percentile of the standard normal distribution. In other words, we want to find the value of k such that p norm of k, remember that's the cumulative distribution function of the standard normal, equals 0.74, or In the uniroot version, it has to be p norm of k minus 0.74 equals 0. In this case, I'm going to define my function outside of the uniroot function and give it a name. So I'm going to call my function fr. Notice it's just p norm of x minus 0.74. And now I'm going to look for a root, and the normal will only have for any percentile, it'll only have one value that gives you that percentile. So I'm looking for this in an interval, and notice I'm doing this differently. In the first example, I gave a lower and an upper. Now I'm doing the other way, which you could have a vector. So somewhere between 0 and 5, I'm looking for a spot where p norm of x minus 0.74 equals 0. Always make sure that your root is in the interval you're looking in, and also make sure that you don't have two roots in that interval. So in this case, if I display GG, once again, it looks like 0.6433465. Notice the $ root. So if I just type GG $root, I'll get the number that I can work with. And if I compare this to Q norm of 0.74, remember they're supposed to be the same. Once again, pretty close. Now, if you have a built-in R probability distribution, you'll have a Q function for that, as we have here, the Q norm of 70.74. So basically, P norm of, so let's look at P norm of 0.74. Actually, P norm of GG $root. And that gives us the 0.74. Notice once again, we have 3 here. So what I want you to bring up here is we found the root directly using uniroot, but there's a built-in function that finds the same thing. You'll find that whenever you have a built-in R probability distribution. Now let's try one more example. In this case, we're going to define a little more general, at least not a built-in R distribution. So here's the cumulative distribution function of a continuous random variable in R. Here's the graph. Notice goes from 0 to 1. And I want to find the median or the 50th percentile of this. That means we want to find the value x so that f of x equals 0.5. Now, if I do f of 0.5, that doesn't equal 0.5. How am I going to find this value? Once again, I can use uniroot. This time I don't have a built-in function. So watch how uniroot works. And in this case, my limit, I know if I use the limits of 0 to 1, I'm going to get an answer because f is only defined in the interval from 0 to 1. And lo and behold, the root is 0.3472. And if I give big F of the root, I actually, in this case, I actually got the exact, it looks like, at least to the accuracy of R, it looks like I got the exact median. And this is how you could use uniroot to solve for roots of simple equations, especially for percentiles for continuous distributions in R.